That makes sense. Makes a lot more sense now.
Yeah, so when you look at vorticity that way and you see that, that's really important that you can help identify vorticity. Do you guys remember there's two types of vorticity in terms of severe weather?
Crosswise, streamwise?
Yeah, and streamwise is when your vorticity vector is aligned with the flow of the wind. So the vorticity rolls like spirals. If it's rolling crosswise, that means the tube is rolling. So you want the tube to roll, to like air through a tunnel. I had a pretty good discussion the other day with my severe weather class. I don't know if they understood anything, but I liked it. So if you ever want to do that, I would really recommend yesterday's 11:15. So that would have been what, November 9th. And if you go to where your class notes are, just go back, instead of 2110, just go to 1115, and you'll see the November 9th lecture. If you want to take a look at that, that would be a really good one if you want to learn more about vorticity and streamwise. And, well, we didn't talk that much about streamwise and crosswise, but you'll see that Lee Orff supercell modeling experiment with the EF5 tornado. It's a talk he gave. I just found this one. It's a great 15-minute lecture. It's really good, but it visualizes vorticity so well. And just to give you an idea of the complexity of vorticity. Funny thing is, speaking of complexity of vorticity, do you understand that vorticity is a change in wind, some sort of wind, over a distance? Okay, the problem with that is that the wind, the distance that you choose makes a great deal of the value of vorticity, right? The smaller the distance, the greater the vorticity. So what we have found that when we do these modeling is we have a good vorticity sense. But when we have a higher resolution model, our vorticity fields get extremely messy. So for instance, if I go over here and I look at 500 mil, I suppose I should share my screen, huh?
Like the difference between synaptic and meso, or?
Yeah, so, okay, you got the screen. So here's your vorticity on the GFS, right? And so there's a lot of little stuff, like all this little things here. These are just small amounts of vorticity that show up there. Are they really significant? Are they doing a lot? You know, from a sensible weather standpoint, from what we're actually experiencing, the answer is no, probably not. Now, there's a good vort max across the Midwest. That's what's creating our system. By the way, just as a side forecasting note, look at the vort lobe. It's pretty much positively or neutrally tilted, and it becomes a little bit more negatively tilted. But do you see how it lifts up into Wisconsin? Whenever you see that big vorticity moving to the north, even though we'll get cold air with the front, our precipitation will not turn over to snow.
Wait, what?
That vort max is not going to be, it's not in a good location to create cyclogenesis. So given that vorticity center, what we're going to say is that the area of low pressure is going to occlude well up to the north in Wisconsin. So any of that wraparound or conveyor belts, the cold or the warm conveyor belts, is going to make a difference only in areas to the north of the vort max. So when I look at precipitation, sorry, I got distracted by Ada or Zeta, or I don't even know what she is anymore. But look at the way it never really comes in.
They said there was a swath of western Iowa that was going to get a 1/4 inch of ice.
Yeah, so watch where we get precipitation type in this area, where we get the ice across Iowa, Minnesota, quite a bit, right? But notice that everything else is rain, because the conveyor belts are going to be well displaced to the northwest. So that defo band of snow stays up for the north. And it should be a pretty decent amount of precipitation. Like if I look at snow accumulations, even though it's not Kuchera, you know, we're talking about the 3 to 5 range maybe. I don't know what the ice is, but the point is we were looking at vorticity. So if I look at some areas of vorticity, and well, I can't do that, but like maybe the NAM nest, no, I can't do that either. I'll do the NAM. See, we took out vorticity at any of those other models because they're so messy. It's hard to see that much detail. Like you get something like this and you get all those little blots. Vorticity is a noisy field, and the higher the resolution, the greater the amount of vorticity when the winds are changed by only like a meter per second, because the distance between grid points is so high. So we had actually done vorticity on the HER, but we can't do that anymore because it's just too much. And so we really don't have anything on the HER that has that kind of resolution.
Too much as far as computation power?
Yeah, because it's too much. You can't read it. The field is so messy, you get spots of red and yellow and green and all over the place because you have positive, negative vorticity because the grid point spacing is so much. It's like saying, why do we get land spouts? Do you guys remember why we get land spouts?
Tense vorticity.
What kind of vorticity?
I believe for land spouts, it's vertical, isn't it?
Mm-hmm. It's pre-existing vertical vorticity, which means we have horizontal shear across a boundary. So if I were to draw a diagram of this, let me go ahead and do this, hold on. New share, I can share a whiteboard. So imagine that I have a boundary of some sort, and I have the winds over here. The winds over here are like this direction, and the winds over here are this direction. So do you agree that's a relatively small change, but there's a boundary. So the question is that there would be vorticity here. Well, how much? How much vorticity exists there? Well, okay, and what if I did something even simpler? What if I said the winds at both places are the same speed of the same direction, but they're 5 knots different? So vorticity is going to be the change in the velocity over some distance. Okay, and please excuse the fact that I'm just using V and X. So I have 5 knots, which is 2.5 meters per second, divided by the distance. Now, do you do the distance from here to here? Or what if I said the winds were here? What if instead of 20 kilometers, I use 10 kilometers? Those stations may be 20 kilometers apart, but is that where the difference of the wind is being experienced? Where does the wind actually change? Well, just by cutting the grid spacing, I have now doubled the vorticity. Do you see how noisy it can be? So the question, and if the winds are gusty and variable, do you understand that the vorticity field is always changing? And the higher the resolution, the less value it gives me for understanding. Because I don't know how big the vortex is supposed to be that's being stretched. So does that make sense to you, what I'm trying to show you, what I'm trying to say to you? Is it depends on the locations that I do it. When I have a model that has grid point spacing, right? And if I'm looking at a 3-kilometer grid point, now we're talking about high amounts of value where the wind could be different. If I had an outflow boundary, I could get huge values of vorticity that show up on a high resolution model. I'm not sure if there's a lot of value to that because it can go one way or the other and it's really messy. So you get it looks like somebody threw up on the vorticity map. So I just wanted to point out that kind of stuff to you, okay? Now let's look at something. Let's go to the book.
Hey, Paul, going right back when you first showed the the model, you called it a Vort low. Is that, I don't think I've heard that term.
Vort lobe. Yeah, Mike, this is from the old days, and it was a lot easier to see, but if I have the contour lines like this, sometimes your vorticity would look something like this. And again, the vorticity back in my early days was a lot less resolution, so it was easier to see maximum values that maybe look something like this. So that would be known as a Vort max. A lot of times, if I have an area of low pressure, I think of this as being a Vort lobe, like your earlobes just hanging down from the center of vorticity here. That's just, I guess that's slang. I've never really even thought of it.
Okay, so if you just see it in the bottom of a trough, you just call it a Vort low.
Yeah.
Okay.
Yeah. So I wanted to talk here. Now, remember I said dVdx, right? Because I didn't care that the winds were southerly or they could have been southwesterly or whatever. Do you understand? I'm just using V as a velocity. I'm not really using UVW, right? Which are your zonal, meridional, and vertical components. And then dx, well, you know, oh, are you meaning a grid that's X, Y, and Z? No. I just kind of meant from here to here. So to avoid that, what we create is what we call the natural coordinate system. Okay, natural coordinates, so that we do away with X, Y, and Z and U, V, and W, and we're just looking at winds. Okay, so that kind of leads me into what I want to talk about today. So if you get your book out, and go to page 271. And they're going to say, and I don't like, why am I doing in pink? That's really an ugly color. Let's go here. V is ds dt. So what we're going to do is we're going to create streamlines. So that's a streamline. Now, how do you define a streamline? Here, I tell you what, you guys got computers too, right? So somebody Google the AMS glossary and do streamline. Because the AMS glossary is a book that you probably should have, or at least know that this is available online if you want to save money.
In line with this tangent at any point in the fluid parallel to the instantaneous velocity of the fluid at that point.
So do you understand that it's, if air's moving in a curve, you look at the instantaneous motion as a tangent. And so we draw streamlines because we're connecting all the tangent lines. We're following the curve. So the streamline is an instantaneous version of the wind field. So we have used kinematics before, which is a vector field. We are now going to use natural coordinates, which say, well, I'm just going to continue as though this is the case. So in other words, I might have winds that here are like this, 10 knots, and over here they're 10 knots, and over here they're 10 knots, whatever. I don't really care. So I look at the winds and I create a streamline. We've all used streamlines in our model products. I've shown you that, so I'm not going to show you anymore. Okay, now if I were to let a balloon go right here, so there's a little parcel, a little balloon, would the balloon follow the streamline? Yes or no?
To the point to where the streamline changes direction.
No, I mean, if I let this balloon go, am I saying that the path of the balloon is along this streamline? Is that how the balloon would travel?
Well,
No.
it would
Why
start
not?
in the direction at that moment in time, but no.
Then what would happen after that, Nick?
The streamline would probably shift.
Okay, so if the streamline shifts, then the balloon at a later point, you know, so if I was over here, let's say, here's the streamline at a later point. Let's say it's a wave that's becoming less. So when the balloon starts moving this way and it gets to here, now which way is the balloon going to move? It's going to start moving this way. And so the path of the balloon will change based upon the fact that the streamlines are different, that they're modifying over the time. What do we call the actual path of the balloon? What's that word? That's her trajectory. So if you have your AMS glossary there, go look at trajectory and then read me what that says. If you
A
could
curve in
grab,
space tracing the points successfully occupied by a particle in motion.
say that again.
A curve or path in space tracing the points successively occupied by a particle in motion.
Okay, so that's what the AMS glossary is?
Yes.
No. Okay, well, that should make sense, right? It's a path that it's actually taking. Now, I know this is jumping ahead and we're not being exactly ordered for what we want, but I'm gonna rewind a couple things here. I want you to go in your book to page 275 and look at figure 7.5. Now, here's something I want you to think about. And this is kind of interesting. And this is what really gets people the first time they hear this, they're like, oh man, that's weird. Okay. What's that? What would you call this if the pressure, if this is Z and this is Z plus delta Z?
It kind of looks like a pressure ridge.
Ridge?
Trough.
So you're saying that the air would flow this way. It's curving cyclonically, therefore it's a trough, right? That's what you would tell me. Okay, here's a parcel of air right there. And it's going to start moving to this direction. Question, what if this air is moving? Now here, you know what? Let me do it this way. Let's put a parcel of air here. You would think it's going to move this way, right? But if the wave is moving faster than the air is moving, at a later point in space or in time, then the wave may be here later. Now, which way is the parcel actually moving? And if at a later time, the parcel is actually over here within the wave, so the parcel starting to move, it's not doing much. Now, which way will the parcel move? So the parcel is actually taking a trajectory that's doing something like this. Which way is the parcel moving?
Anticyclonically.
That's not a trough. If the air is actually curving in its trajectory anticyclonically, well, I'm not saying that it's not a trough. There's certainly a pressure trough, but the parcel's motion is anticyclonic. So now take a look at figure 7.5. And go ahead and read that. James, would you read that for me, the figure 7.5?
Sure. Streamlines and trajectories for parcels in a wave moving eastward with phase velocity c embedded in a westerly flow with uniform speed u.
Okay, so a couple things right there on that first one is we tend to use capital U as the scalar or the scale quantity for air speed. In other words, that's wind. Remember we talked about scaling is about having orders of magnitude, like powers of 10. So we use U, capital U, to determine that. C, they say, what do they call C? What do they define C to be?
Phase velocity.
Phase velocity, right? Or phase speed. Well, that's really what that is the speed of a wave. In meteorology, if we are looking at a short wave coming across the United States, then that short wave will have a phase speed of c. The wind flowing through the wave will have a velocity that we assign to be an order of magnitude. I mean, we could be specific and say the winds are moving at 32 knots, but we are saying that there is a speed of the wind, and then there's the speed of the wave. Now, where else have we seen C? Where else have you seen C in science?
Speed of light.
Right? Speed of light. But isn't the speed of light the phase speed of electromagnetic radiation, which is a wave? So when I'm actually looking at velocities of something, and you can see this in the future if you go on into meteorology, you're going to see phase speed, wave speed, and you're going to use actual wind speed. So James, continue on.
All right. Solid black arrows denote initial streamlines, and dashed black arrows denote later streamlines. Blue arrows denote air trajectories from a starting point. A for 3 different values of U. AB is the trajectory for U, which is greater than C.
So let's take a look at that, right? AB is the trajectory for when U is greater than C. So we start at some point, and where are we starting? We're at the base of a trough. A to B is saying that the wind is traveling faster than the wave, which means that the location of the parcel of the air will be further along the wave because the air is moving through the wave. Did you guys? Are you able to understand me when I speak in English like that?
Mm-hmm.
Say that back to me. Nick,
That back to me.
Funny. Say that back to me then. Tell me what A and B in your own words.
A and B is where, or A. So A and B or A and B, because there's A, B, and then there's
A to B.
Okay, A to B.
What happens when the velocity of the parcel is moving faster than the phase speed?
Okay, and if that's the case, the parcel is moving through the trough, right? Imagine the trough's not moving. The parcel would just go around a cyclonic arc, right? So the parcel is moving through the trough. As long as it's moving faster than the trough is moving, it's moving through the trough somewhat, right? Relative to the trough, it's going to be further downwind. Now, it won't be as far downwind as if the trough had not been moving. So the actual path is going to be of a less amplitude than the contour lines or the streamlines would show you at any given point. So when we are going to, and we're going to be talking about calculating wind speeds based on the curvature. Do you understand that if I showed you a trough, you could tell me what's the radius of the trough? Really what I need to do is show you the curvature of the parcel, and now you know the centrifugal force of the curving parcel, not the trough itself. So if you're going to get sub and super geostrophic winds, you're going to need to know how much the curvature of the trajectory is, not of the streamline. right?
Mm.
Now, what is A and C? The wind is moving at the same speed as the wave speed.
Wave speed.
So where does the partial start relative to the wave? In the bottom of the trough. Where will that partial be later?
In the middle of the trough.
No, still in the bottom of the trough, right?
Oh, I see what you. Okay.
So if you look at letter C is in the bottom of the dash trough, right? It's in the, or as Roger Edwards, the basal part of the trough, the base of the trough. Now, where is A? A is in the trough. If the wind is moving slower than the trough, then when it gets to letter D, do you understand it is now upwind of the base of the trough?
Mm-hmm.
Which means the trajectory going from A to D is anticyclonic. From A to C, it's going linearly. From A to B, it's going cyclonically.
So if the situation is AD, then that's actually a ridge.
Well, no, but because the trough and the ridge is the pressure field, right? It's a trough.
Okay.
But the flow of the air is curving anticyclonically, which means it's super geostrophic.
Okay. Are UNC typically assumed to be constants?
No, no. I mean, you're just, in order to visualize it, it's a whole lot simpler if you think of it as constant.
Yeah.
But it makes, do you understand? That's why modeling is so much better, because modeling doesn't care. It's doing, see, a numerical model will do what they call finite differencing. So they don't do calculus, right? They just go, they do what they call time steps. They go, here's the velocity currently. Here's the forces acting on the air now. Let's run it forward 5 seconds and tell me where the parcel is. So in that 5 seconds, we're assuming there's no changes. We don't know what that change. The rate of change is 0 in that 5 second interval. But at 5 seconds, we know, okay, here's where the air has gone. Here's all the things that have changed. Now let's reinitialize the model and look at where the parcel will be 5 seconds further. That's called time steps. The model time steps. And obviously, the smaller the time step, the better the model will be. But the greater the calculations will be, because you have to do a lot more calculations. So, but since a model does it, it doesn't really care that much, right? It's like, right? Understanding this concept of time stepping is like looking at this. Do you agree that this is a curved line? A curved line is much more difficult to draw. A computer does what? It draws straight lines. So it goes from here to here, and it's going to draw a straight line. And then maybe the next time step is from here to here. And then the next time step is here to here. And then the next time step is from here to here. And the next time step is from here to here. Do you see, that I'm getting close to a, well, whatever. I'm getting close to the curve. It's not exactly the curve, right? And chaos theory says this initial conditions must be exact, or else things will fail in the future. So so what I try to do is make the lines smaller, the time steps smaller, so that I might do something like this. I'd go from here to here, which is going to be a lot better representation of this curve, right? Smaller lines, it looks a lot closer to the curve. It's still not exact, but it's closer. It's more precise. So since a computer can do that, we don't worry about that too much. We know that the wave is modifying, but in the model world, it will realize that it's modifying and therefore adapt. But when I'm dealing with forces, and I'm dealing especially with forces like the centrifugal force, which is V squared over R, I'm really going to use the radius of trajectory, not the radius of curvature of the isobars. It's what's the parcel actually doing. But that should make you understand how difficult it is to look at a weather map and know what the year is actually doing, because it changes. Now, Mike, would you go ahead and read the, well, actually, yeah, go ahead. Why don't you read 7.1.4, streamlines versus trajectories?
All right, if the horizontal wind field V is changing with time, the streamlines of the instantaneous horizontal wind field considered in this section are not the same as the horizontal trajectories of the parcels. Consider, for example, the case of a sinusoidal wave that is propagating eastward with phase speed c superimposed on a uniform westerly flow of wind u, as depicted in figure 7.5. The solid lines represent horizontal streamlines at a time t, and the dashed line represent the horizontal streamlines at time t plus delta t after the wave is moved some distance eastward. The trajectories originate at point A, which lies in the trough of the wave at the time t. If the westerly flow matches the rate of eastward propagation of the wave, the parcel will remain in the wave trough as it moves eastward, as indicated by a straight trajectory A to C. If westerly flow through the wave is faster than the rate of propagation of the wave, uniform is greater than the phase speed, the air parcel will overtake the region of southwesterly flow ahead of the trough and drift northward, as indicated by something trajectory A to B. Conversely, if the uniform is the speed is less than the phase speed, the air parcel will fall behind the trough trough of the wave and curve southward eastward as indicated by AED.
Hey,
By contrast,
hold on a second. Yeah.
no.
Oh, yeah, what kind does it need?
Rest in peace, Alex.
Any idea who the new host? They have any indication who's gonna be the host?
No clue.
Yeah. No. He's irreplaceable.
You know what? You were doing some pretty good reading there. I could nominate you if you want, Kevin.
Ooh. Is it safe for us to go get coffee?
Maybe.
I vote yes.
Therefore, is it unanimous?
Go for it.
All right, make a run. Can't fire us all.
Well, I guess my internet thought it was a good time to go out there. And frankly, it was.
Yeah, much worse time could have been had.
Yeah.
Timing is everything.
Yep. Thank goodness for whatever the heck was going on in Paul's construction project.
Sorry, guys. Just had some questions I had to deal with. Okay.
As I was telling him, Paul, my internet went out right in the middle of that, so it was perfect timing.
Good deal. So now when you read that, paragraph, does it make a lot more sense? Because sometimes when you're reading it alone and you've got this diagram, you're like, I don't know, what the hell are they talking about? Does that make sense to you now?
Yep.
Yep.
Okay, so now we want to go back to this V, because now we're going to make some more sense of this. So anything that's along a streamline is the velocity. So how fast I move from, let's say, here to here. I would say, well, what that is I'm moving along a streamline, and I go a certain distance along the streamline. That distance that I travel is ds. Now, obviously, we could think of this as being an infinite distance along the streamline over an infinitely short amount of time, but that's what velocity is. So does that make sense that the velocity is now ds dt?
Mhm.
But I'm also going to use in here a line that is going to be perpendicular to the streamline. And we're going to call that n. So now we go back to page 271. And we're going to say that n is a direction to the right of a streamline. So what I'm saying is that along the streamline, this is S along the streamline. This is N this way. Normal. Right, what are the three words that mean perpendicular? Perpendicular, normal, and what's the third?
Orthogonal.
Orthogonal. So when you look at the definition and back on page 271, it says at any point on the surface, one can define a pair of axes of a system of natural coordinates, S and N, where S is the arc length directed downstream, and N is the distance directed normal to the streamline. And toward, oh, wait a second. And toward the left. I'm sorry, I lied. Actually, I didn't lie. I made a mistake.
N should be the other direction.
N should be the other direction.
Oh, n should be on the left side?
Yes, it's directed to the left.
Silly question. In the southern hemisphere also?
I don't know the answer, but I don't think so.
Okay. Not that I'll ever care.
Right. Not that you would ever care, but for instance, you know, just to give you some idea, imagine that I've got a set of isobars going this way. Do you agree that the velocity of the winds is this way? So that's S. Now, if I do S hat, what does that make it?
A unit vector.
Right. Okay, so that's the S direction. Then N would be to the left, and that would be N hat. So which force points in the N hat direction? If these are isobars and this is geostrophic wind, what are the forces acting on the geostrophic wind?
Oh, duh.
Pressure gradient?
Pressure gradient force is in the N hat direction. And then what direction is in the negative N hat direction?
Negative centrifugal force.
No, not centrifugal.
Coriolis?
Coriolis force. So we're going to have the Coriolis force. Okay, so we have the N, the positive N is just to the left. So I got that wrong. Anyway, so that's what that is. Now, one last thing on this page. The direction of the flow at any point is denoted by the angle psi, which is defined relative to an arbitrary reference angle. So in other words, God, let's see if I can do this. Let me use a different color. And I'm saying, here is the flow, the tangent at this point. And then over here, we have a vector pointing this way. So that this angle between the changing velocities is psi. And how do you, psi is PSI, right? Psi?
Right. Now that can be an arbitrary angle based on how you define X and Y.
Right. Stream function. So if you ever see that, do you have your glossary up again? Look under stream function. And there's different uses of this, but I'm gonna actually use my computer too. AMS glossary stream function.
Not found.
Yeah, no, here it is. Let me share my screen with you there.
Stream function or stream
Stream function.
hydrograph?
Are you guys seeing this? A parameter of two-dimensional non-divergent flow with a value that is constant along each streamline. So the stream function psi is related to the respective coordinate velocities u and v by the equations. U is negative the change in psi with respect to y. So we're gonna try to understand a little bit of this. They also have something known as the Montgomery stream function, which is this. You know, when I started grad school, we did Montgomery stream function. I had no idea about. Not only did I know what that meant, I had no idea what this meant. I never knew what anything was. I was so confused because I didn't have that enough meteorology to be good at it. How I got through grad school is a joke. Luckily, I figured stuff out later. Okay, so a new share. Let's go back to the whiteboard.
Is psi the wave function?
Not a wave function, a stream function.
Okay.
So what we want to do is, and I'm not going to draw this out to you, but let's look at table 7.1, because this is where things really go on. So the first one is shear. So I'm going to erase all of this, clear all drawings, and I'm going to say I've got a streamline. Like this. And it says it's the change in the velocity in the n direction. Okay, so the velocity at this point is going to be the tangent at that point. If I go into the n direction, okay, that means the velocity over here is less. Does that make sense? So this, again, keeping in mind what I mean, and if I hope you understand, that is the S, oops. That is the S direction, and that is the N direction. So what is the velocity doing? It is getting smaller as I travel in the N direction. That value is negative. That makes this positive because shear is dV dN, but it's negative dV dN. Because do you agree that that shear will cause what? Why is there a negative sign in here? First of all, what is the velocity doing? Because look at this. This here is a question. How does the velocity change as I travel in the n direction? What is the velocity doing as I travel in the n direction in this picture?
Decreasing.
Decreasing. So dV dN, so the value inside the parentheses is negative. But a negative makes it a what?
Positive.
So this would be defined as positive shear. Why do you think that is? Why is that positive shear? Like, why do I throw the negative sign in there? Why isn't it just shear? Use your right hand and show me what happens. What does your vorticity vector do?
Pointing up?
It would be
No.
pointing up. Okay, well, up is positive. So when you create positive vorticity, then the shear should be positive shear.
Positive.
Okay, so by the way, we have natural coordinates, which is S, N, and what do you think the third one would be?
Z
It's going to be K.
or K, IJK.
Um,
If you're dealing, yeah, if you're dealing with unit vectors.
yeah, so. Because up is up, no matter what. Okay, so what is this next one where it says curvature? It's V d psi ds. First of all, let's look at units. What would the units of curvature, well, actually, what are the units of shear? Do you agree the units of shear is meters per second per what? Per meter. So it's just S to the minus 1, which is a what? What is it, Nick?
Frequency?
Frequency.
Well, when something is rotating, wouldn't you say that the amount of rotation is frequency?
Mm-hmm.
Shear results in vorticity. That makes a big difference.
You know, ever have days where you just suddenly cannot write anything down and you have to like rewrite everything because your writing is so terrible?
Yeah, every once in a while I get minutes like that. So what's the unit of velocity?
Too much caffeine.
Unit of velocity is meters per second. What's the unit of a change in the angle?
Radians.
Well, it would be radians, right?
Right.
But radians,
Per meter.
what do you know about radians? Is unitless.
Right.
Or dimension. What you would say is non-dimensional. There's no dimensions to
Dimensionless.
dimensionless, unitless, whatever you want to say. And then S is a distance, so it's going to be divided by meters.
Meters.
So again, it's S to the minus 1. So curvature results in vorticity. We talked about absolute vorticity is curvature. So what makes something curve more? If I'm here and then a little bit later I'm going this way, do you agree that that's a bigger angle as I go from here to here? Now, if I went from here to here and I did the same change in the angle, do you understand that's a longer S that makes it less curved? But then what else makes it curve more depends on how fast I'm traveling through it. So if I'm going really slow, that's very little curvature. If I'm going really fast, I'm curving a lot. So curvature is V d psi ds. Now let's talk about diffluence.
No.
It's a fun word.
Now we've already talked about what divergence is, right? We say that divergence is speeding up along, like, would you agree that this is divergence? But in natural coordinates, what is this?
Acceleration?
Well, no, well,
dv
yeah,
over
yeah.
ds.
Do you agree it's dvds?
Yeah.
Mhm.
Because
Oh,
as
yeah.
I'm traveling, it's going faster. The velocity changes as I move along a streamline.
Right.
Well, look what dvds is in the table.
What table are you looking at?
Stretching.
It's stretching. Well, isn't that what we said? Divergence is stretching something. So really, dvds is what we call a stretching term. So diffluence, though, is if I have air that's doing this. Do you agree that this is it's flowing apart, even if the velocities are the same? So what's happening is I have, let me use a different color. What I have here is I have, the directions are all the same. Here, the direction's changing. But what makes it diffluent is the fact that this direction and that direction are different. So the direction, psi, is changing as I travel which way? In the n direction.
Direction.
But how much would that be? Velocity times it. Because once again, I now have a unit of per seconds.
You only take the top of that. You don't consider the bottom of that.
Well, in either way, but this is still positive diffluence, right? Because the angle is going in the opposite direction as I go in the opposite direction. Those are both negative, makes it positive.
So diffluence would be the top plus the bottom, if that makes sense.
Well, no, because it's just the magnitude. Like here,
Okay, so it's just a
what I'm
scalar.
saying,
Okay.
as I go from here to here, right? As I go from there to there, what's changing?
Right.
The angle as I travel
Right.
this way. So there's a degree change. So
Right.
let's say it's pi over 8 degree or pi over 8
Okay.
radians as I go north. Over here, how much do I change by? Pi over 8, but it's negative. But
That's
I'm
right.
traveling in a negative direction.
Right.
So it's the same number. And if I double the distance, I'm doubling the angles. 2 over 2 is canceled out. Does that make sense?
Oh. Yeah, okay.
So that's what's known as diffluence.
So they always assume diffluence is symmetric about some streamline?
Yeah, well, it doesn't, I mean, I'm just illustrating it. It's just,
Okay.
it doesn't have to be symmetric. It's just saying it's the way that it changes. Vorticity now, we know the vectorial is del cross V, right? But if we're talking about horizontal, I want to do K dot that. And then divergence is del dot V. Or yeah, del dot V. So we know this to be true, right? But in natural coordinates, look at divergence. Divergence is V d psi dn plus dv ds. But what is V d psi dn called?
Diffluence.
And what is dv ds called?
Stretching.
So divergence as a quantity is actually the combination of both diffluence and stretching. Now, this is what has always bothered me, and Tom Skilling does this too, and he's just not right on this stuff. So I'm going to show you something that we often say. Here's an upper level trough. And in this upper level trough, we have a region here of a jet max. So in this jet max, we are talking about strong wind speeds. But also in this upper level trough, oops, let me do this. We are looking at a jet stream that does this. Now, Tom Skilling will always say things like this. He goes, there's a whole huge amounts of divergence here. When you come out of a jet and you get this big spreading out of the isobars, Tom would say there's divergence and that draws the air up. Is that true? What is actually happening in this region here?
Diffluence.
It's diffluence, which is part of the divergence term, right? But what is happening here where the winds are faster than they are, let's say, here? Is that stretching?
It's the opposite.
It's convergent, isn't it? And we can't say convergent even though that's what it is, because it's the opposite. So really what you would say is negative stretching or shrinking or something like that, right? Which means that this term can be positive toward divergence. This one is negative toward divergence. So it's negative divergence convergent. So then the question is, when I add the two together, what actually happens? Is the air divergent or is it convergent? Which is more? Which of those two terms is more in this picture?
Divergence.
Well, here, do you understand what I'm saying? Is so let me see if I can make this easier for you. Divergence in natural coordinates is both diffluence
That's what looks.
and
Diffluence is very great. Looks great in that.
stretching.
Greater.
So when it's diffluent, like it is in this picture, then we know that that's a positive term. But do you see that it is converging in terms of speed because I have a jet max coming into here? So that means this is negative. So this term,
Greater than stretching.
this term is acting opposite from this term. So which one's bigger? If diffluence is more than stretching, negative stretching, then it will be divergent. But if this negative stretching is more than the diffluence, then it will be convergent. And if we're talking about upper level winds, is the air going to be forced down or is it going to go up? And the answer is, well, you don't just know that. You'd actually have to calculate it. Now, sometimes in a scenario like this, you actually get convergence aloft, which would say what to the air below it? What's the air going to be doing below that if it's convergent? It's going to be sinking.
Sinking.
And if it's sinking, well, is that good for thunderstorms? And the answer is, well, it doesn't really matter. But what happens is you will get a Cape robber. Because what does sinking air do?
Generally condenses, converges.
Sinking air.
For more stability and it could be warming.
Well, it would be stable, right? It'd be warming and stable. That's what a Cape robber is. So the high level of your Cape will do it. But we're going to show you later on that it doesn't really matter what the upper level air does for initiation of storm, because storms initiate from the bottom up, not from the top up or top down. Anyway, I just wanted to show you that. So then the last terms in here are what we call deformation terms. So do you have any questions on this? Does that make some sense to you?
So just to be clear, the negative stretching is negative towards divergence, right?
Mm-hmm.
Okay. That was written a bit weird there, so I wanted to make sure I had that right.
Yeah. There's this little negative sign underneath it in blue. It's negative stretching. So it's making it convergent. See, that's why you got to be careful about this. Sorry, got something important going on. Okay, are we all good on this stuff?
Yes.
Mm-hmm.
All right, so let's look at this last term, du dx. So now we have to look at this. Du dx minus dv dy. Draw that picture.
Similar to what we went through last Thursday.
And as I travel to the north, the velocity should get what?
Increases, positive.
Stronger?
Yeah, positive, right?
Weaker. No,
Should get weaker.
decreasing.
Minus, right? It's minus in there.
Ooh. First term.
And then the other one is dv dx. Plus du dy. So what does that look like? dv dx. So the hold on. dv, dude, seriously, what did I do here? dv dy is what? I'm going to say that there is a y component. And as I go to the north, what should it get? Less.
Stronger. Yeah.
Okay, so in this example, if I were to put a square around this, what is this square going to do? What will this side of the square do?
Pull a little to the northeast.
Won't I stretch it? And then what will it do with the meridianal one?
Shrink.
Crush it. So I'm taking this square, and with those vectors in place, what will this square look like a little bit later?
Rectangular. Yeah.
Rectangular. So what that says is, what am I doing to this polygon? I'm deforming it.
Right.
I'm changing the entire shape of it. Now, what about this guy down here? dv dx. So this, oops. As I travel in the x direction, like that, and then du dy. So the u changes. And then now what would I do with my square in this case? What would this square become?
A larger square.
No, wait, think about this. Do you agree that I'm this side of the square would do what? Would move that way. What would this side of
Right.
the square move? Less.
Oh, it's going to be a larger
And then this side of the square would move more, and
That
this side
way.
of the square would move less. So that means my square is not a square.
But it's a rectangle that's larger than the original square.
Well, wouldn't this cause it to turn?
Oh.
This
I
side
see.
turns the other way, and it's going to stretch it out. So in other words, what we want to do, now we want to look at which one would be a good one? A deformation. We're deforming it. So let's take a look together at page 273. At figure 7.2. So how would you describe letter A using natural coordinates? That would be what?
It's a negative du over dy.
Well, I mean, how would you just how would you describe?
Oh, in words?
Yeah, like what is that?
Shear flow without curvature.
Isn't that just shearing? So that's
Oh, okay.
the
Yeah.
velocity as I'm traveling in the n direction, dvdn. What about B? Do you agree that the V is changing as you go into X? So dv dx is going to be positive. And then what's du d? Oh, that's a tough one. What's du dy? What's du dy there? Like go from the center of the circle to the north.
Hello, this is an important message from the Illinois Department of Revenue. We show that you have not electronically filed all of your withholding returns. To avoid additional penalties, please submit your
Who is
IL-945
that?
as soon as possible. Visit mytax.illinois.gov.
Is that you, Jim?
Yeah, sorry.
That's a dangerous spam call.
But fun.
Okay, so and so as I travel to the north, what is you doing?
It's increasing,
U.
then gradually decreasing.
No, starting from the center of the dot going to the north.
Oh,
It's going to be the change in u is going to be negative as I go
Mhm.
positive, but it's getting more negative. So the one that's on the screen in my shared screen, that's negative du dy. And that's going to be what? Rotation. Now, what does that do? It says solid body rotation with cyclonic shear and cyclonic curvature, hence cyclonic vorticity, but without diffluence or stretching and hence without divergence. So that's solid body rotation. Now, we did this in 1115. We did kinematic fields where we talked about something going solid body. And the reason for that is at the center, it's going to go slower, so it's like a record player. Now, what's letter C? Letter C is pretty obvious. That's simply pure kinematic divergence, but there's something else going on. It's not just divergence. What else is it doing?
Accelerating.
So it's right.
Stretching.
So it's stretching also. So it's diffluence and stretching. So if you look at this, it says this flow exhibits diffluence and stretching and hence divergence, but no curvature or shear and hence no vorticity. So what would a square do? And now that's the one, Jim, where the square just gets larger. Now, what's going on at letter D? First of all, what do we call letter D? What do we call letter D?
Well, it says hyperbolic flow, but I'm assuming you're looking for something different.
Convergent boundary.
Okay, so what I want you to think about is what's going on here. What's going on in that axis? Based on that axis, what's the air doing?
Converging.
Converging, right? So it's convergent along that axis. But what's happening along this axis?
Diverging.
It's diverging. So depending on the axis you're looking at, it's either convergent or divergent. Now, if you were a parcel of air, which way would a parcel of air be here? It would flow this way, and then it starts to converge. It could go that way, it could go that way, right? So it's going to get stretched. So think about this square. This square would become more what? More like a rectangle. I'm sorry, it's a little bit off. Whoops. No, I want to turn it a little bit. I don't know if I can. Well, whatever. It's just, sorry, I didn't mean to be crooked a little bit. So do you see that it's divergent along one axis, stretching it out? Do you agree it's being stretched? So I want you to think about something, and this is just a totally random thing. Imagine that I have isotherms here that look like this. Cold air to the north, warm air to the south. Do you understand I'm putting warm air this way and I'm bringing cold air this way? So what will happen to the gradient? Nick?
Looks like it should probably sharpen, right?
Right, so the gradient increases in temperature, but what do you call that?
Front.
Frontogenesis.
Or frontogenetic.
Frontogenetic.
So that would be frontogenetic. And this is what's known as a call point, or like a saddle point. So you have flow that's this way, this way, this way, this way. That's a call point. So, and the idea of this, what's another name for a call point? Does anybody know? Called a saddle point. Anybody want to know why?
I would like to know why. Why is it called a saddle point?
Okay, if I draw a saddle, this is what a saddle looks like. Your legs are going over the saddle, so you're sitting at the high point. But from front to back, you're sitting at the low point. Right? So a saddle looks like this. When your legs are around it, you're sitting on the ridge if you go across the horse. If you go parallel to the horse, you're on the trough. So that's what's going on here. Is this area of low pressure or high pressure? In the middle, it's this low, well, it's convergent, so the air is converging toward low pressure, but it's divergent, so it's diverging from high pressure. So just so you understand, that's the axis of, right? So that's what's known as a saddle point. A saddle point is both the maximum and a minimum at the same point. All right, I'm going to teach you a little calculus. Does that make sense to you? So, by the way, this is just a deformation. So, you know how we call the defo band, the deformation zone, the defo band of snow? The deformation band is like this in the atmosphere. It's a col point. You see a 700 millibar col point, you're going to see strong frontogenesis. And if you have strong frontogenesis and you're increasing the gradient, you're going to get rising air, and that's where your heavy snows are going to be. But I want to talk to you something about this. If I have a curve that's like this, what is the value of the tangent at that curve? And again, I'm sorry, because I'm writing on a...
I'm assuming it's supposed to be completely flat, right?
Right, flat. So that's the zero
0.
point, right? So
Mhm.
how do I know what that is? Well, if I have a function of x and the first derivative is 0, then we know that we're at a minimum or maybe a maximum. Because what if I did this? What's the tangent at this point?
It's also 0.
So the first derivative being 0 tells me the value is either a maximum or a minimum. But look at the tangent to these points on the curve. What is the tangent doing here? It's going from a negative slope to a 0 slope to a positive slope. So the way that the slope is changing as I travel in the x direction, it's going to go from negative to positive. And what's the slope doing here? It's positive going to 0, going to negative. So what I do is I take the second derivative of a function. If I'm going from negative to positive, then the value of this is greater than 0. It's a positive change. Over here, it is less than 0. So if you ever look at a function of anything and you look at the first derivative and it's 0, that tells you you're at either a max or a min. When you take a look at the second derivative, if the value is positive, you're at a min. If the value is negative, you're at a max. So look at this saddle that's over here. Do you understand the saddle is both a max and a min? At the same point. That's what makes it a col point. Okay. Now, let's look at page 274, 7.1.3. Who would like to read that paragraph?
Sorry, what page again?
274, 7.1.3. It says deformation.
7.1.3. Gotcha. I can read, I suppose.
Okay, go ahead.
From the beginning.
Yep.
Deformation, defined in the bottom of table 7.1, is the sum of the confluence and stretching terms. If the deformation is positive, grid squares are oriented along the S and N axes and will tend to be deformed into rectangles, elongated in the S direction. Conversely, if the deformation is negative, and the squares will be deformed into rectangles elongated in the direction transverse to the flow. In Cartesian coordinates,
Cartesian. That's XYZ. Cartesian, right?
Cartesian coordinates, the deformation tensor is made up of two components. The first relating to the stretching and squashing of the grid squares aligned with the X and Y axes, and the second with the grid squares aligned at an angle of 45 degrees with respect to the X and Y axes. Figure 2.7d shows an example of a horizontal wind pattern consisting of pure deformation in the first component. Here, the x-axis corresponds to the axis of dilation, or stretching.
Dilatation. Dilatation.
Dilatation, okay, or stretching. Never seen that word before. And the y-axis corresponds to the axis of contraction.
Okay, so looking at the diagram on the whiteboard, the east-west is the axis of what?
Convergence.
Convergence.
No, but no, the axis of dilatation or contraction. What's going on that axis? It's convergent, but what are you doing to it? You're stretching, so that's dilatation. The y-axis is contraction.
Sorry, what's the question again?
Looking at the diagram, where is there contraction? It's along the x-axis, right? You're contracting along that axis, but the axis of convergence is the y-axis. I'm sorry, the axis of contraction.
Stretching.
It's contracting along the y-axis, right? It's contracting along the y-axis. Along the x-axis, what are you doing?
Stretching.
The x-axis is the axis of dilatation, or in this case, east-west, dilatation, contraction. Keep going. James?
Oh, sorry. This is someone who's outside my door for a second. I'm sorry. All right. If the wind patterns were rotated by 45 degrees relative to the x and y axis, the deformation would be manifested in the second component. Rectangles would be disformed into rhomboids.
Okay, so what we're saying is if we change it by 45 degrees, rather than going from a square to a rectangle, we're now going to go a square to a rhomboid. We're gonna kind of shear it, so to speak. Hey, go on. We don't need to worry about that. Go on. You'll see.
Figure 7.3 illustrates how even a relatively simple large-scale motion field can distort a field of passive tracers, initially configured as a rectangular grid, into an elongated configuration in which the individual grid squares are stretched and squashed beyond recognition. Some squares that were initially far apart end up close together, and vice versa. Deformation can sharpen pre-existing horizontal gradients of temperature, moisture, and other scalar variables, creating scalar variables. Creating features referred to as frontal zones. To illustrate how this sharpening occurs, consider the distribution of a hypothetical passive tracer whose concentration psi, yeah, that's it. Psi xy is conserved as it is carried around or advected in a divergent free horizontal flow. Because d psi over dt equals 0.
Over. How dare you do that? Say it right.
D psi dt equals 0 and 1.3. It follows that the time rate of change at a fixed point in space is given by the horizontal advection is try again. At a fixed point in space is given by the horizontal advection. That is.
Stop for a second. So what we're saying is, imagine that what we have over here is this checkerboard square. And the only reason they have that checkerboard square is because they're saying there might be something in each box. Let's say each box is air of some temperature. That's a scalar quantity, right? So it starts out at letter A, and the flow is kind of in those streamlines that you see around an area of low pressure, right? I mean, you've seen that. That's not new to you. A little bit later, what's going to happen? A gets deformed. Some of it's stretching, some of it is being pulled apart. And so the air gets really funky looking. Look at what happens at letter C. Stuff at the bottom of letter C starts to go around the area of low pressure. So that by letter E, so rather than thinking even temperature, if I put little squares of ink, this is what the pattern would look like. And since that pattern of air is talking about, I mean, the pattern of squares is all talking about air molecules, the air is really going all over the place. And so the pattern of this becomes so incredibly complex. I just think that's really cool to try to take a look at. So now they're going to say, okay, this is given by horizontal advection. So let's think about this. d psi dt. What does that mean? d psi dt.
How the angle changes over time.
Okay, so that the orientation of the vector of which way that streamline is going is changing over time. And then that's going to be equal to what? The velocity times what? What is that? What's del psi? Use your words.
How the angle changes.
Well, what is del operating on a scalar?
Oh, how the angle changes
What's
in
del
3 dimensions.
operating on a scalar? What do you call that?
Oh, duh. It's a scalar.
Correction.
No, can't be.
Wait,
Del operating on a scalar is called a what? You have it in your notes. What does it say? What is del operating on a scalar? Del is an operator. Nick,
it's a vector.
no,
Oh, it's a gradient.
it's a gradient.
Duh.
It's
Oh,
the gradient of the angle. And then what do you call velocity times a gradient?
Velocity.
Acceleration.
Vector times a gradient.
The velocity times a gradient is called a what?
Acceleration.
No,
No. The field.
called advection.
Advection.
When
Oh.
you have a velocity times something, it's advection. If you have a temperature gradient and there's a velocity field acting on it, that's an advection term.
Velocity times pretty much anything is advection.
Yes. So this is the
All right.
advection of the gradient of the directions. And so they go, well, let's look in Cartesian coordinates. The time rate of change of psi at a fixed point is positive if psi increases in the upstream direction, in which case v must have a component directed down the gradient of psi. So you need to spend a little time thinking about what these things are. So let's take a look at the diagram on 7.4. Okay, now we already said A is what? When I showed you the picture of A, what would you say this is?
Frontogenesis.
Right, it's frontogenesis, it's frontogenetic. All right, let's look at what happens at letter B. You've got cold air moving to the south, and you get warm air moving to the north. And so what are you going to start to do? Aren't you going to start to spin that around? Isn't that what happens when I have a cyclone? The warm air gets advected and wraps around, and the cold air wraps around. Isn't that what leads to an occlusion?
Yeah.
So these are just ideas and concepts that you need to think about. Now, I skipped a whole section. So go back to page 272 really quickly, if you would, please.
And I can already feel I'm going to be coming back to this for my final project.
Yeah, this is tough. This is not easy stuff, folks. Now, we've talked about vorticity and divergence. We said that vorticity is going to be twice the angular momentum or angular speed, blah, blah, blah. We've talked a little bit about that. Work it through, that's fine. But then there's a divergence term, and there's this weird, funky math. And so I need to spend time with you on Thursday going through this math. So, and I'm not going to do second integration. So I'm not going to do vorticity and the circulation. So I'll skip the page. I'll skip that stuff on 274. And then we're going to get into other things. But I need you to do something for me. So I'm going to stop. I'm going to stop this share. And I'm going to go over here. Do I have any other videos on Blackboard besides the mechanical universe?
I've got it up. Let me check. I don't see anything besides the mechanical universe now.
Hold on. I have it under class notes. Oh, you're right. Okay, so what we need to do is I don't know if this is gonna work. Eulerian and Lagrangian description of fluid mechanics. And there is a video. Sorry, I'm just laughing at this one. But that is what you need to do. So I'm going to do this for you guys.
So just like look like right at the camera so we can see the reflection of the screen in your glasses will be good.
Oh, hold on a sec. I forgot that I wasn't sharing my screen. But I don't need to because I'll let you find this on your own. Chat. Here. Everybody should have that, so go ahead and copy the link. It's called the Eulerian and Lagrangian description of fluid mechanics. Just so you know what it looks like.
Bring that up for later viewing.
This is what it looks like. It's bad quality video. Eulerian and Lagrangian descriptions in fluid mechanics. There you go. Copyright 1960 something, 68. So that's, that's only 50 some years ago.
In order to calculate forces exerted by, specifically, we'll be interested in describing the displacement, velocity.
Okay. My students hate this movie, and we're going to see it multiple times. But it is absolutely foundational for you to understand how some of these things work. So that little description of the derivatives in there. So what I want you to do is I want you to watch it once. And the first time you go through it, I don't want you to take notes. I just want you to stay awake and just try to pay attention to it and get the gist of it. Then on Thursday, I will go through some of these techniques, and then we're going to go through the video together. And then you'll go through the video and really get serious about trying to figure this out. But I'm guarantee you, you want to learn about fluid mechanics, this is it. So in case you haven't figured out, we are serious engineering geeks over here. But it's really, really cool. Sorry, it's a black and white movie. I wish somebody did a better one, but it's not. But that's what you'll be doing, okay?
Yep.
So don't freak out if you don't understand everything. It's going to take some time to get there, okay? But enjoy the movie, you guys. It's interesting. And then we'll have one more black and white, which is a lot more exciting. It's called Waves and Fluids.
So we just need to watch this movie before Thursday then.
That's right. And then, study your book and you work on your project, your final project.
Yes.
How's that coming? Are you making progress on it?
Progress is being made, yes. Oh, that actually reminded me of the question. It's probably on somewhere, but online. But what day is it due? Because I'm going to be going to work right after this. And I want to request a week off beforehand, just so I have a week to.
Is the due date on there?
The 13th of December, right?
13th of December, I think. Yeah.
I believe.
All right, I was going to request the week before that off, just so that I can make sure to fully dedicate my time to this before the end.
You're a smart man, James. All right, guys. I will see you on Thursday.
See you on
Bye,
Thursday.
guys. See you Thursday.
Another one of those classes where it was tough, but I feel like I actually made some progress in learning something, so it feels good.
Excellent. Okay, have a good one, Mike. We'll see you guys later. It's a lot of new stuff, but it's fun. So we'll talk to you later.
Take care.